Section 10.5 introduces polar coordinates. We have already looked at graphing with parametric curves, meaning we have a curve that's defined parametrically, but we still graph it on the XY plane. And we're going to look at something similar today. We're going to deal with points and then functions, polar functions that we can then write in Cartesian form today. But in the next section, we're going to be graphing them as polar functions. And then the section after that, we're going to be doing calculus with polar functions. So when we do polar coordinates, there's a lot of trig applications, meaning if you are not familiar with the unit circle and the values of the basic sine, cosine, tangent on any of the quadrantal angles or the special right triangle ratios in terms of radians, then this would be a good time to stop this video and to go back and review those, because it is really important that you know those, okay? All right, so polar coordinates, when we write an ordered pair, it's going to be r comma theta. R indicates distance from origin, so in other words, r indicates the radius, okay? And then theta indicates the angle of rotation counterclockwise from the positive x-axis, which if you think about back in trig when we drew like reference angles and stuff like that, that's really the direction that we always started with, where we start with this positive x-axis and then we open up this direction. So theta is going to be that angle. So let's draw our axes, okay? And these are the xy axes, meaning when we put a point that is given, that is defined in polar terms, okay, so this is the point r theta, it still has x and y coordinates, like it's graphed on an xy plane, but its location is described in terms of its polar function, okay? So what we're talking about here is r is the distance from the origin. The origin here is called a pole, okay? So this distance here is r, and then the angle of rotation that opens from the positive x-axis, like I mentioned up there, by the way, this is called the polar axis. The positive x-axis is the polar axis, okay? This angle here is theta, okay? Now, this ordered pair, like I said, it does have x and y coordinates as well. Okay, meaning we could drop that down and then describe it in terms of where it is on the xy plane. This distance right here is x, this distance right here is y, because this is the same thing as xy. Now, we also know from the unit circle that we have some identities that relate using SOHCAHTOA that relate r and theta to x and y. So we know that x is equal to r cosine theta, okay, and y is equal to r sine theta. All right, so these should be things that we remember, again, from trig. So this point is the ordered pair xy, but it can be converted between polar coordinates and rectangular coordinates using these identities plus a couple other identities. So other identities that we know, also from SOHCAHTOA, we can say that tangent of theta is equal to, so tangent of theta, opposite over adjacent, is y over x. And then also, because this is a right triangle, we can say x squared plus y squared is equal to r squared. So using these four identities, we can do a lot of easy conversions between polar coordinates or polar forms of either points or functions and their Cartesian counterpoints, okay? So let's look at a couple of points. We're going to do some plotting, and these are given in polar form, and then we're going to give the Cartesian counterparts. When we graph, we want to start with theta, okay? We want to start by looking at what is the angle of rotation from the polar axis, and then once we figure out what our angle is, then we count out that far to whatever the radius is going to be. So in other words, when we graph like xy points, we always count the x first and then the y, but in polar coordinates, you need to start with the angle, okay? So start with theta to plot, okay? So x-axis, y-axis. So this is the point 5 comma pi over 2. Well, pi over 2 is this much right here, so we are opening upward. And then if we go up 5 units, okay, then this is the point 5 comma pi over 2 in polar form, okay? And then we can go ahead and give the rectangular coordinates, because I think we know what that point is. That's the point 0, 5 in rectangular coordinates, okay? Because it's just straight up the y-axis. And then for this next one, the point 2 comma pi over 6. So we start by opening up pi over 6, which is about this amount right here. So this is pi over 6, okay? And then we want to go 2 units out. So really it probably would only be about right here. So this is the point 2 comma pi over 6. Okay, and then let's go ahead and convert that to Cartesian, to its Cartesian counterpart. Okay, so we know we can draw a little right triangle. Switch colors. So I'm going to drop down this vertical piece right here. Zoom in. Okay, so this is, whoops. So this is pi over 6. This distance right here is 2, so that's actually the hypotenuse of this 30, 60, 90 triangle. If you want to change it to degrees, that's fine, as long as you make sure that all of your answers, when relevant, are in radians, okay? And we know that we have ratios of 1 to 2 and root 3 to 2, okay? So, let's just make those bigger. 1 and root 3, okay? Because this is 2, okay. So then this point in Cartesian form is going to be the point root 3 comma 1. Okay, now before we go on to another example, I have a question about the second point, okay? And that second question is, what other polar points are root 3 comma 1? In other words, what are some other polar coordinates that actually land in the same place, or that we could, ways that we could label the same point in polar form, okay? And a couple of ways that we can do that. One way is that we could say, well, what if we added 2 pi to our angle, meaning instead of just opening by pi over 6, we wrapped all the way around and landed in that same spot? Well, all the way around would be 2 pi plus another pi over 6, so that would be 13 pi over 6. So we could say that 2 comma 13 pi over 6 is another form of this same point, okay? Another option is we could go the other direction. So if we have a negative theta, then we are opening this direction. So we're going all the way around except for pi over 6, meaning we could say the point 2 comma negative 11 pi over 6 would land us in the same spot. Okay, and then those two are fairly obvious, but there's another option as well. And the other option is we can count, make that smaller, we can count the radius as a negative as well. If I consider this angle right here, which is 7 pi over 6, that's just a straight angle from the pink radius here. This angle is 7 pi over 6. Okay, so if I open this much, but then I count a radius of negative 2, then that lands me back right here. Okay, so the point negative 2, 7 pi over 6 is still that same point. So make sure that that makes sense to you. If we are opening all the way up to a ray that comes this direction, but then we count the distance from the origin with direction included to be negative 2, well then if this is the positive direction, negative 2 would come back this other way, and so the point negative 2, 7 pi over 6 lands us there as well. Okay? So we do have a few different ways that we can label a single point if we are using polar coordinates. Okay? For this example here, let's give the polar form of the Cartesian point negative 1 root 3. Okay, so negative 1 root 3, let's go ahead and graph that. Negative 1 root 3 is going to be somewhere right around there. So this is negative 1 to the left and root 3 up. Okay, so then if we're trying to figure out what this point is in polar coordinates, then we need to look at what this angle is. I'm drawing a little reference triangle here. What this angle is and then what that length is. Okay, well, we know from special right triangles that this is going to have a distance of 2. Okay, and then this angle, well, this angle right here is pi over 3. So that means, make it a little bit bigger, that's pi over 3. That means that this angle here is 2 pi over 3. So in polar coordinates, we can write this ordered pair as a radius 2, comma, angle 2 pi over 3. All right, and just like we saw before, we could, in these examples here, we could write that differently. Like, for example, we could say, well, let's do negative pi over 3 and go this way, but then count a radius of negative 2. So negative 2, comma, negative pi over 3 would land us in the same space. Okay? Or, you know, wrapping around more than once. So there's actually an infinite number of options, which means just like in trig, we usually have some kind of limit on theta. Like we say theta is between 0 and pi, or 0 and 2 pi, or negative pi and positive pi, or something like that. Okay? All right. When we are graphing polar equations, we have two different options. We can either graph them as polar functions, which we are going to do in 10.6, but our option for today is we are going to take these using the identities up above, and we're going to change them into Cartesian form first. Okay, so just a refresher, we are using these four identities. X equals r cosine theta, y equals r sine theta, tangent theta is y over x, and x squared plus y squared equals r squared. Okay, so we want to do some kind of rearranging so that we can get each of these to use one of those forms. Okay, so in other words, try to get an X or a Y form out of these. All right, I'm going to call this one part A and this one part B, so I can label my work here. So for part A, we have R equals 4 sine theta. Okay, so pause it, take a second, and see if you can write something that might look like one of those identities. Okay, I'm guessing you tried to use something where like y was equal to r cosine or r sine theta, okay? But we don't have another r here. Well, I could get another r here, not by moving this r over, because that's not how algebra works, but what I could do is I can multiply by r on both sides of this equation, and then I end up with r squared equals 4r sine theta. Now the reason that I would want to do this is because I know from my identities that this is the same thing as y, and that also this is the same thing as x squared plus y squared. So now I can replace both sides of this equation with an expression in terms of x and y, okay? Which gives me x squared plus y squared equals 4, that's just a coefficient, y, and then to graph this, now I need to figure out what kind of a function is it, or equation is it, and how do I graph that? Well, I've got an x squared and a y squared, both with a coefficient of positive 1, and so this is going to be a circle, okay, so we're going to complete the square. So x squared plus y squared minus 4y equals 0, so that's x squared plus y minus 2 squared, and then we need a plus 4 minus 4, or plus 4 on both sides. Either way, we get equals 4. So this is a circle of radius 2. Okay, circle of radius 2 with a center at 0, 2. Okay, so this graph would be, call that 2. Do my best to draw this in a somewhat circular fashion, which is not easy with this pen. Okay, so something like that, not quite circular, but you get it. If you're graphing circles, here's a trick. If you start with the circle and then put the axes on top of it, it looks a little bit nicer, okay? But I did not do that. All right, so there's the graph for the first one. For the second one, we've got r equals 4 over 2 plus 2 sine theta. Okay, I would recommend that you pause it and give it a shot first. I am going to recommend that you might need to reduce something somewhere first. Okay, so pause it, give it a try, and then resume. Okay, so to reduce this, I'm going to take a 2 out of all of those. So now I have 2 over 1 plus sine theta. Okay, rearranging this, I'm going to multiply both sides by this denominator. So I end up with r plus r sine theta is equal to 2. Okay, and then using identities, r sine theta again is equal to y. We had this in the last one as well. And then r, using the Pythagorean identity, using the Pythagorean theorem, we know that r squared is x squared plus y squared. So I'm going to write this as the square root of, so this is root x squared plus y squared. Okay, so I get root x squared plus y squared, and I'm going to move this over to the other side, equals 2 minus y, and then I'm going to square both sides, so x squared plus y squared equals, and then squaring this side, I get 4 minus 4y plus y squared. Rearranging, let's see, y squareds are going to cancel out, so I end up with x squared is equal to 4, actually let's write this differently. Let's write negative 4 times y minus 1, because I know you guys like to have that y in front of the constant, right? Okay. So what kind of a function is this? Or what kind of an equation is this? This is a parabola. We could look at this in this form right here, or we could write it in the way that we're more familiar with from Algebra 2. So I could divide by negative 4 and then add 1, so I end up with y equals, or actually let's leave the negative 1 there. Y minus 1 equals negative 1/4 x squared, okay? Or you can add 1 behind that and get rid of this over here. So negative 1/4 x squared plus 1. Okay, so this is a parabola. Okay, we know that it is going to open downward, and we know that it has a vertex at the point 0, 1. Okay, so that's our vertex. And then let's see, for graphing, oh, p-value. Okay, so p is, this right here is 1 over 4p. So that means 4p is equal to negative 4, meaning p is equal to negative 1. So since p is negative 1, equal sign there, then I know that I have a graph with a vertex at 0, a little bit higher, at 0, 1. Okay, the focus is going to be at the origin because it is 1 unit below here, and then the directrix would be at y equals 2. So there's our directrix, and this opens downward, something like that. Okay? So when you are graphing, if it is points that you're plotting, then in polar form, then change those. You can, look for the angle first and then plot the radius along that segment, okay? And if you are graphing equations, then one option here, the one we're doing today, is to change them to Cartesian form first.